Welcome to Unit 3. Today we talk about the cross product. Let me introduce that first. So today I will mostly write the vectors as column vectors. So for example, if we have the vector 3, 4, 5 and the vector 1, 1, 1, what we have done is we have produced a scalar from this by multiplying the components and then adding them up. 3 plus 4 plus 5 would be 12. That would be the dot product. But we want now to have a vector. This is called also the vector product. And we write a cross here. Let me just tell you what we do in order to compute this. So one way to do this is to write the first two components again here, and these two components again, and then make three crosses. So here 4 times 1 minus 5 times 1 is minus 1. Let me just write that kind of down here. This is minus 1. The second component is when we do this. So let me just make this green here. The second is when we do this cross here. 5 times 1 minus 3 times 1. 5 minus 3 is equal to 2. So this gives me the second component here. And then the last component is when we do that here. 3 minus 1, 3 minus 4 is minus 1. So that's the last component. So that's one way to compute this cross product. It's called a cross product or vector product. You can also think about it in general when we have a V1, V2, V3, cross it with W1, W2, W3. What we can do is, I'm just doing the same thing in here, but in more in generality. What we have is V2 times W3 minus V3 times W2. And now the rest is all cyclic, so that becomes V3, that becomes V1, that becomes W1, that becomes W2, that becomes V1, V2, that becomes W3, that becomes W1. So this is the general definition for a cross product. It's a little bit strange at first. It's really a little bit, it was hard to find by Hamilton in 1843. Same Hamilton who has kind of he defined quaternions and was in the same time actually introducing the cross product and dot product. I will tell more about Hamilton in the lecture. A very interesting personality. So that's the definition of the cross product, and you will compute this a lot during this course. So I'm not making any more example, but I just start with properties here already. So one of the kind of strange properties is that if we take V cross W, this is not W cross V. So that's property number 1 here. And it's not true here. But you might guess when you look at the expressions here, what happens if you change W and V, so that V2 W3 becomes the W3 V2, and that becomes a negative sign. So you see that it's actually a negative sign here. So this is called anti-commutative. Which is a little bit weird. It actually has to do with physics. A lot of these things have to do with physics we will see in applications. This is a product which appears a lot in physics. But it has some strange properties, and it's only defined in 3 dimensions as such. Now the second property is kind of very important for applications, is that V is perpendicular oh, W cross V, this new product is actually, this new vector here is perpendicular to V, and W is perpendicular, of course, also. So the picture is like that. So we have V, we have W, we are always in space here, and this V cross W is a vector which is here, V cross W, which is both perpendicular to V and perpendicular to W. So that's the claim here for the second property. But actually, I can just do that on the same blackboard here. If you look at this here and multiply this with, I'm reusing here this thing, and multiply this, how do we see that something is perpendicular? Perpendicular means, you should recall that from last time, perpendicular means the dot product is equal to 0. And that's really what we do here. What we have to show is that we take V1, V2, V3 and dot it with that. What do we get here? So we get this, that's V1, V2, V3. So what we get is, let's just write this out all. So this is V1, V2, W3 minus V1, V3, W2. And then the second part is plus V2, V3, W1 minus, I put the V2, V1, W3. And then the last part is plus, this is V. V3, V1, W2 minus V3, V2, W1. And now the fun starts. Now it's Candy Crush time. Candy Crush time means you have to look for things which cancel out, that fall away. V1, V2, W3, where is that? You might spot it, there are 6 expressions here. Candy Crush. And there is another thing, V1, V3, W2. V1, V3, W2. Candy Crush. And finally, the V2, V3, W1, V2, V3, W1. Candy Crush. Isn't it nice? So we have this beautiful cancellation, and actually we proved this property here. Okay, property number 3 is this one. It's a very cool property, and actually also relates here something algebraic with something geometric, and we will see it actually relates to area in a second. But let's just see how we prove this. So there is an identity called the Cauchy-Binet identity. Which says that V square W square is equal to V times W square plus V cross W. So I'm not going to prove that here. I will prove that in the lecture in a few seconds. But I'm not doing it here by purpose. You will see why in the lecture. So this is a very beautiful identity. It's an algebraic identity which doesn't involve any angles. Now, once we have that, we already know what this is here, right? This is actually just V. From last time, we know that this is equal to cosine square alpha. Now we can take that on the other side, and we see that V square W square times 1 minus cosine square alpha is just equal to V cross W square. Now you should know this identity is one of the identities you have to know from trigonometry. 1 minus cosine square alpha, 1 minus cosine square alpha. Pythagoras is sine square alpha. So this is V square W square times sine square alpha is equal to V cross W square. And now we take the square root, V times W times sinus alpha is equal to V QD. Modulo this thing which we are going to prove in class. But this is very nice. This is a very nice thing. So we have another relation here between, and note that the angle is always between 0 and pi, and so the sine function, if you look at the sine function from 0 to pi, so this is always positive. That's why we have here a positive root. We don't have a problem with plus minus here, so that works pretty well. So this spans a parallelogram, and we have this. Now this is almost immediate here, because we have W times sinus alpha, right? So this is as a geometric interpretation here. W times sinus alpha. This is the height, and this is the base here. So if it's base times height, that's already the Greeks knew this, right? You take this part and cut it here, so you get the rectangle of height h and base length of v, and so that's the area. So there are already geometric applications. We have seen area. We can compute area very nicely. We can also compute volume. We will do that afterwards. But let me just mention a couple of physics applications. So first of all, there are forces which you can describe using the cross product. So one of them is the angular momentum. So if you have something turning, like here, it's a little bit hot here, so we have this fan. So that turns around, and you can actually compute the angular momentum of this using this formula here. So not that you have to know this, things is from physics, but just as a motivation. And then we have also torque. I will also say a little bit more about this and show a little movie about this in the lecture. Then there are forces like the Lorentz force. Let me see whether I get that right. It's r prime. We can also write velocity cross magnetic field. So this is called the Lorentz force. I will actually show you a motor, how a motor works. The principle of an electric motor is like that. So you have a magnetic field, you have an electron moving in a magnetic field, or some charged particle in a magnetic field. This is the charge, and so this is a force. So the particle will actually move on a circle like that if the magnetic field is constant. So this is a Lorentz force, and there is also the Coriolis force, which is a little bit strange, which is V cross W. W is the angular rotation. I will also illustrate this a little bit more in class. So this is Coriolis force, and so on. You can find many more applications of this in physics. So, but it's a little bit a strange product because you see that actually this thing. If you take something like a wheel and you turn it around, and then you are keeping kind of try to move it, you actually see there is kind of a strange behavior. Something unintuitive happens. There is a force perpendicular to it, which you might be familiar with, And the angular momentum conservation is also quite of a important thing. So, for example, when you are biking, so that you stay stable. So, if we have three vectors, then we define a parallelepiped. So let me just draw that here. So we have one vector v, we have another vector w, and then we have a vector, a third vector u. So this defines what we call a parallelepiped. First of all, there is a parallelogram here. And then, let me just make this maybe blue here. So this is the vector u, goes here, here, we take that, and we have a... So this parallelogram has been translated up here, and this again here on the top. So what we call this a parallelepiped. Now I draw that also from the side so that it's a little bit easier. So this is the easier to see here. So let's assume here this is this parallelepiped here, and then here we have the vector u, so that we can draw an angle, and then we take this angle here, alpha. Now you all know the formula for a parallelepiped. It's the base area times height. So the volume is base area times height. Now the base area we have already computed, right? So this is the base area is just v cross w length. That's what we have just done. Now we have the problem to find the height. Let's just draw this height here. So this is the height here. The base area was yellow. Now what is the height? And so we can read that off here. So that's u. So it's the length of u times, now you have to think, what is this? If this is a right angle here, is it opposite or adjacent? And you see it's a sine alpha which comes in. So it is the length of u times the sine alpha. So that's what comes in here. Now we are almost there. Because we know, sorry, what did I do here? Yes, so that's actually true. That's actually true, but it's the wrong way to think about it. So the way how we have to think about it, so I leave that in the video because it's actually might be quite useful to have this little, because that's always a little bit confusing. So what we have is here, this is actually v cross w. And if you look at this, that's that vector here is perpendicular to it's perpendicular to the plane here. So that's actually the vector which goes perpendicular up and is giving us the right direction for measuring the height. So now, but if you have u and v cross w, then we have not this vector which I drew there. So, but I have this vector here. Maybe I write it with beta here. So this vector here is actually the vector which we can do. So let me just do it again. So the volume is base area v cross w. So that's the base area times the height. Now using the vector beta, what is the height here? So now we look again at this triangle, and so it's the length of u, but now we are adjacent, it's cosine of u, cosine of beta. So this is the length u times cosine beta. So that was a dead end. Actually doing it again here, because now we are not in a dead end, because we know what this actually is here. We can get rid of this, and what we have is seen is we have a vector, the length of a vector, the length of another vector times the cosine of the angle between them. That's actually nothing else than u dot v cross w. So we have a very nice formula. So the volume of a parallelepiped is u times v cross w. Now we take the absolute value, because this could also become negative, and actually this has a little bit of relation whether this is parallel. This vector u has an acute angle to v cross w or not, so that depends on the orientation. So if we have a plane here, let me just actually kind of introduce a plane like this as all the, so this is a vector n. Let's take this vector 3, 4, 5. Now, how do we characterize a plane? So let's assume maybe this is the origin here. This is the coordinate system. So we are in space, and we have two points here. The first point here I call x. Here I call this x naught. This vector I call x naught here. And this vector here, this is vectors, these I call, so let me just actually use only vectors. This vector I call x here. So x vector is just as the coordinate x, y, z. So these vectors go from the origin here. So these are also coordinates. And so this is x0, y0, z0. Now what we can do is we can look at the difference between these two vectors here. So this is the vector x minus x0. Now this vector is, if we are looking at the plane, this vector is inside the plane, and that motivates us to define the following thing. So we take the plane as all the vectors x which have the property that x minus x0 is perpendicular to n. So we define a plane so x minus x naught dotted with n is equal to 0. So this blue vector is perpendicular to that vector here. So that's what we assume to be a plane. And let's just write this down. So x is x, y, z. So if we take that and multiply that, let's just write this as ABC. And let's take this as x0, y0, z0. So what this means is x times n is equal to x0 times n, which is just a number. And what we have here is ax plus by plus cz is equal to d. So this is the equation of a plane. And you can in principle forget what we did here and just look at that. But there is a lot of benefit if we have this if we have this picture because we know that this vector ABC is perpendicular to the plane. Good, that's the theory. Let's just look at the very typical example. It's very hot, we don't have air conditioning. So let's just look at the example. So take 3 points. A is equal to 3, 1, 2. B is equal to 1, 2, 1. And C is equal to 4, 3, 7. And the question is, find the equation of the plane through these 3 points. So, this would be an impossible problem without that theory which we have. We have this theory which tells us, oh, why don't we look at the construct a vector perpendicular to it? So what we can do is we can construct this vector here, which is minus 2, 1, minus 1. And then we can construct this vector here, which has the components 1, 2, 5. And now we want a vector perpendicular to it. So we want this vector n, which has these components a, b, c. So how do we get this? Now comes the cross product. That's the application of the cross product. We take the cross product between these two vectors here. So n is equal to minus 2, 1, minus 1. I just take I take here column vectors because it's a little bit easier to write here. In the notes I usually use row vectors, but here on the blackboard it's often better to use this. So why don't you do it on your own quickly and see whether you get the same thing. Done this, and we have done this, minus 1 plus 10 is 9, and then finally we have minus 4, minus 1, minus 5. So what we have is we can just write down the equation of the plane is so what we have is 7x plus 9y minus 5c. And now comes the magic. We want to find this constant d, which we have. So just take one point and stick it in. So the d here you get by just sticking one point. It doesn't really matter which point you put. For example, if you put in 1, 2, 1, you get a 25, a 20, you get 20. And you can maybe double, if you want to double check, you can put 3, 21, 30, minus 10 is also 20. So our equation is 7x plus 9y minus 5c is equal to 20. So that's the kind of one of the fantastic applications of the cross product, that we can immediately get equations of planes and solve such problems without linear algebra. That's it for unit 3.